Hello everyone. My name is Aditya Nair. I'm an assistant professor in the Department of Mechanical Engineering at University of Nevada, Reno. In this lecture, I'm going to present some reduced order modeling techniques for unsteady fluid flows. So let's begin. In lecture 1 of the series, we talked about dynamical system-based representation of the flow equations. We just reiterate some of that dynamical state representation of high dimensional variables on the slide. In lecture 2, we talked about dimensionality reduction techniques, in particular modal decomposition of high dimensional data. So if you recall, the particular decomposition that is shown here is that of separation of variables in the temporal coefficients, which evolve over time, and the associated spatial modes from the proper orthogonal decomposition technique. Now, strictly speaking, the dynamics of the state, which is governed by this function f, may not strictly lie in the subspace or in the region that is spanned by these POD modes. So if we want to find the subspace that is closest to the dynamics of the state f, we can perform an orthogonal projection of the function f using this operator p. Okay, so let me recap. So we have the state dynamics, we do the modal decomposition, but because strictly the dynamics of f may not span the subspace of that's spanned by the POD modes, what we want to do is we want to do an orthogonal projection such that we basically find the subspace that is closest to f that is spanned by the POD modes. So what happens is if you substitute this modal decomposition in this projected reduced order or projected model, what you end up getting is a reduced order model. And the reason why we are getting this reduced order model is because we know that POD modes are orthogonal, right? So on substitution, what happens is, because these modes have this nice orthogonality property, you actually now get an ODE model governing the time evolution of the temporal coefficients A, right? So what happened is we started with a state dynamical system that governs a PDE, and we ended with a simple ODE based dynamical system that describes the evolution of the temporal coefficients of the modes, right? So this is really powerful. So this technique is called as Galerkin projection. All right, so let's look at the exact mathematical framework for Galerkin projection of fluid flows. Now, the state dynamics of the conservation of momentum equation can be converted to a reduced order model by expanding the velocity field U as a summation of spatial modes or POD modes and temporal coefficient. Now, if you recall in the last lecture, I mentioned that we need to subtract the mean before we perform POD. So we can also think about, I is equal to 0 mode here being the time averaged flow or the mean flow, and the associated temporal coefficient being forced to be unity or 1. Right? So that's the same as, because the time averaged flow does not have any time varying component to it, we can fix that coefficient to be unity. So this way we get, I do not have to track the mean separately from all the modes of the flow while constructing the Galerkin projection reduced order model. So when we perform the Galerkin projection, so we substitute this U into the state dynamics, what we end up getting is, some quadratic terms. You can see the quadratic terms that comes about is in this inertial forces and the pressure forces. And you see linear terms appearing in the viscous forces term. Okay, so now we have converted this complex PDE representation of the state dynamics by doing this POD decomposition and substituting it, and using the fact that POD modes are orthogonal, we get this really nice ODE representation of the system dynamics, of the temporal coefficients. And once you have the temporal coefficients, you can always go back and reconstruct the full high dimensional flow field. So a quick recap on first doing POD. So let's take an example of a flow past a cylinder at Reynolds number of 100. As you can see, there is an instantaneous snapshot of the vorticity field in A. We show the time averaged vorticity field in B, and we get these spatial modes which appear in conjugate pairs. Remember, this is a low Reynolds number flow, so we are going to see maximum amount of energetic structures as being mode 1 and mode 2. So mode 1 and mode 2 are the most energetic structures, then mode 3 and mode 4, and so on and so forth. And you can see the energy from just looking at this phase portrait of A1, A2, and you can see a larger radius for A1, A2 compared to that of A3 and A4. All right, so we did this proper orthogonal decomposition. So now we substitute these modes and we get a Galerkin projection model. So how does it perform? Now, in this slide, we show the evolution of the temporal coefficients in the limit cycle regime of this flow, where we get, unsteady vortex shedding. So you can see these nice periodic oscillations of each of the temporal coefficients, and there is excellent agreement of the Galerkin projection reduced order model with the DNS data, essentially, or the true data, right? But I want to emphasize the fact that the initial condition here was chosen to be on the limit cycle, right? So the natural question that one may ask is, what happens if the initial condition is not on the limit cycle? Well, if the initial condition is not on the limit cycle or outside the limit cycle, Galerkin projection method starts to reveal some problems, okay, or some of its problems. So now if the POD modes themselves are insufficient to reproduce the true dynamics of the system that start from the initial condition outside the limit cycle, the Galerkin model kind of struggles because it lacks the information of the other modes that might be energetically or dynamically important for such a transition to happen. So the figure shows, an evolution of the temporal coefficients from what is called as the unstable equilibrium or the unstable steady state of this flow. And we can see that the Galerkin projection model overestimates the saturated limit cycle. So you can see on top in red, that is the Galerkin projection model. And the Galerkin projection model actually overestimates the limit cycle. So the saturation, where the saturation happens, actually the limit cycle where it happens, it's much larger than what it truly is from the DNS data. While performing something like an extended dynamic mode decomposition really recovers the true underlying dynamics of the system well, or the evolution of the system from the unstable equilibrium well. So the extended dynamic decomposition is what we discussed, in the last lecture, and that really does a great job in terms of, in terms of the system evolution from off attractor or off limit cycle behavior. So we see that though Galerkin projection is a great tool when it comes to modeling limit cycle behavior, it sometimes can be sensitive for off-limit cycle behaviors. All right, so before we go into other reduced order modeling strategies, so we discussed one, which is the Galerkin projection model. I want to give you a quick recap on, again, data organization. The high dimensional data in X is X, and the low dimensional data is Y. The columns of X and Y are just different temporal realizations of the flow or your measurements. And the rows of X are the spatial points and the variables that are of interest. And the spatial rows of Y are different features. Now, the measurement model for Y is usually given by this general function H, which maps the outputs, which are Y, to the states, which are X. So before we discuss some useful models for predicting flow behavior, let us first understand linear regression. So we have this measurement model in the last slide where Y at a particular time was related to the state of the system X through this function H. So now suppose we want to extract a linear model for the relation between the output and the states. Here Y is the dependent variable and X is the independent variable. We can write this model as Y is equal to X multiplied by C, where C is the coefficient matrix. Now this can also be written in the form of a minimization problem where we want to minimize the error between the observed Y and the model. The model is XE, right? We discussed, a very similar setup when doing DMD, when doing Koopman decomposition, the autoencoders. We had very similar structure in formulating it as a cost minimization problem, right? Or an optimization problem. So how can we obtain these coefficients, right? So we can obtain these coefficients by solving the matrix equation given here. And this matrix equation is also called as a least squares equation, right? So this is the closed form solution for getting these coefficients for the linear measurement model or your linear regression model, right? So now if the independent variables, which are X here, so this could be your snapshots of the flow, your different flow variables. Now, if they are highly correlated with one another, which is often the case in high-dimensional fluid flow data, then what we can do is we can regularize the problem by adding some positive elements to the diagonals. Now, what this does is this increases something called as the condition number of your regression method. Now, this type of regression is called as ridge regression, and the regularization method is referred to as Tikhonov regularization. Now, this is quite a popular trick even in machine learning algorithms to improve the condition number of regressors. All right, so now that we understand linear regression, we can discuss a really popular method for discovering models for nonlinear dynamical systems called sparse identification of nonlinear dynamics, or SINDY. So the intuition behind SINDY is that if we have a nonlinear dynamical system of some state, say X here, we can write the continuous time derivatives of the states of the system described by a library of basis functions, theta of X, multiplied by coefficient C. So you can see this is kind of the same form as that, the simple linear measurement model that we had in the last slide, but where the left-hand side is now replaced by the continuous time derivative of the states X, and the state matrix X is replaced by a library of basis functions, which now I haven't told you how to construct the library, but it can be the library of basis functions multiplied by coefficients, right? So these library of basis functions in general can be generally constructed in different ways, right? So to get the coefficients C, you need two things. You need to compute the time derivative of the states of your data, which sometimes may not be possible if you have noisy experimental measurements. And you also need to construct this library of basis vectors or basis functions. The choice of the library vectors, just like in the case of the Koopman analysis, regulates the accuracy and robustness of the model. So in most cases, polynomial expansions of the data can be used. Even sine or cosine transformations can be used to formulate this library term. So once the library terms and the time derivatives are computed, one can actually perform the regression to get the coefficient C. Now, this gives a really nice interpretable nonlinear model for the state dynamics. However, these coefficients could be dense and could lead to poor performance accuracy of the model. So to promote parsimony or sparsity between in the coefficient space, what we do is we do something called as sequential thresholding. What that means is we threshold the small entries of the coefficients. So we essentially remove them if the values are smaller than a certain threshold. And then regression is performed again and again. And if you keep repeating this procedure, the model coefficients will essentially converge and you will end up with a really sparse model. Now, I want to emphasize that the modular nature of this sparse identification algorithm in designing different libraries as well as the simplicity in terms of constructing a sparse model is what makes this a very exciting approach. So this plot is from the original paper on SINDY, where the methodology was applied to the Lorentz system. So the Lorentz system exhibits a really nice butterfly manifold. Of course, we know what the true dynamics of the system are in this case, but we want to recover these dynamics on the right-hand side in terms of the sparse regression methodology. So once again, you compute the time derivatives of these three state variables, x, y, and z on the left-hand side, and you construct a library of terms. Here polynomial terms suffice because we know that the true dynamics has polynomial terms. And we then perform sparse regression to solve for the active terms of the dynamics, and we get the coefficients associated with the appropriate library that matches the true Lorentz system really closely. So what we end up seeing is the model coefficients are really, really close to the coefficients of the original Lorentz system. Next, this approach was demonstrated for PDEs as well, where snapshot data from the fluid flow was collected. And in this case, the vorticity field of a flow past a cylinder was collected. Then time derivatives of this vorticity field, either from numerical simulations or the time history of the data, were computed. And the library terms that was used in this case were spatial derivatives of vorticity and velocity and polynomial multiplications or multiplications of these spatial derivatives. And then sparse regression was performed again to appropriately compute the coefficients associated with the true system dynamics. And what we actually see is the SINDY procedure is able to recover what was the true PD of the system, which is the vorticity transport equation, another form of the Navier-Stokes equation. All right, so we saw earlier that the Galerkin projection model overestimated the modal coefficients. So can SINDY reproduce the correct limit cycle dynamics from evolution of for the evolution of flow past a cylinder from the unstable equilibrium? The answer is yes, but we need to add some constraints to SINDY. In particular, if the coefficients of the SINDY model are also required to satisfy the energy conservation of the flow. So if we enforce energy conservation of the flow, that is number one. And number two is we increase the order of the polynomials in the library to being cubic, then excellent agreement of the SINDY model with DNS is obtained. Now this cubic order of the polynomial is quite curious, right? Because the Galerkin projection model that we obtained had a quadratic nonlinear term. So somehow these cubic polynomials are providing some kind of closure model for off limit cycle evolution of the flow trajectories. All right, so now we will discuss some more intrusive data-driven reduced order modeling techniques. Now, I say these are intrusive because they need access through the original governing equation or the ability to perform some impulse response studies on the true governing equations of the nonlinear dynamics. So you get more than just, representations of what the base flow is doing, but you also get some relations between an input forcing to the system and the outputs of the system. So in some sense, you get more information, but it doesn't come for free. What you actually need is access to the original governing equations, or like I said, the ability to perform impulse response studies in a systematic manner. So the first one that we'll discuss in these class of intrusive models is the eigensystem realization algorithm. For the eigensystem realization, we are going to assume a linear state space dynamical system. Now, to obtain this linear representation, you can think about linearizing the Navier-Stokes equation. Now, in this state space representation, you see a matrix, which is the linearized operator of the governing equation. You also see this BU term, which is the control term. And you also see this y is equal to cx, where c is the measurement matrix, the linear measurement matrix. So the main idea behind the eigensystem realization is to find a reduced order state space representation for the same inputs u and outputs y. So everything else in the system can change. So A, as you remember, if it's a linearized governing equation, this is fairly high dimensional. So we want to find a low dimensional A tilde, say, representation of the system, some low dimensional states, say X tilde of the system, low dimensional input matrix B tilde, and low dimensional measurement matrix C tilde. But we want to keep the inputs of the original system as well as the outputs y the exact same. So we essentially, in conclusion, for this system, we want to basically maintain the input-output relationship in the system dynamics of the reduced order model. So to build this reduced order model, what we are going to do is we are going to build two Hankel matrices, H and H prime. Now, H and H prime can be thought as the time-shifted matrices, just like in the DMD case. So it's built the exact same way, but the entries of this Hankel matrix are going to come from impulse response studies performed on the original system. So we are not going to just collect the data of the original system. We are going to add some impulse perturbations, some impulses in U, and then we are going to measure the different state outputs of the system, Y, and then we are going to assemble this Hankel matrix H and H prime. Now, once we build this Hankel matrix, what we can do is we can perform the rank truncated singular value decomposition, and then again, through similar tools of the DMD methodology, we can build this representation, the A tilde representation, the B tilde and the C tilde, which basically represents the reduced order model for describing the same input-output dynamics as the original system. So in some sense, you can see that though this method is intrusive, now there is the added complexity of having inputs and some relationship to outputs that can be modeled really well with this eigensystem realization algorithm. So let us see an example for this, for a flow past a flat plate. We see that on the top is just shown a configuration and some time average flow for this flow past a flat plate. And on the bottom is shown the impulse response of the leading POD mode of the velocity field. So the outputs here, we want to model the entire velocity field. So the outputs is taken as these POD coefficients of the velocity field. And what we see is just by taking 10 POD modes, and by performing this, eigensystem realization algorithm, we can get a really nice, agreement with the direct numerical simulations or your true data. So in some sense, you still retain this input-output relationship now. So if I just performed an impulse response, for example, in the Galerkin projection, it may not give the fidelity of the response that the POD modes are doing in this eigensystem realization model, reduced order model framework. All right. So we talked about the first intrusive model, which was this eigensystem realization model. The second model that we are going to look at is what we call as the phase-based model. Now, from the name, we can think about, the phase-based model is describing the phase response dynamics of the unsteady fluid flows. So you'll see that quickly when, in moving towards the intrusive techniques, I start to use the word response more, because most of these techniques have, not only the regular baseline flow dynamics, but it also has this aspect of control inputs affecting the system dynamics as well. So we always talk about this in terms of some response of the flow dynamics, of the unsteady flow dynamics. So again, this is an intrusive data-driven technique. Also, the phase dynamics of the oscillation can be explained. So the phase dynamics, which is theta dot, can be explained by the natural frequency of your oscillatory flow and a product of what is called as the phase sensitivity function, so z of theta, so it is dependent on the phase of the system, and a time, and the product of that with the external forcing f of t. So the first question that you may have is, okay, how do we simply describe the phase of oscillation of a periodic flow? So what we can do is we can look at the phase portrait of the lift coefficient and the time derivative of the lift coefficient. And you can see that as the flow evolves through different stages of vortex shedding, we get different phases of the flow along this limit cycle. So the question becomes, how do we extract the phase sensitivity function? Well, for this, we can add some impulse perturbations to the system. So we're going to do, similar techniques to what we did in the ERA. We're going to add some impulse responses. And these impulse responses are going to be added in particular directions of the flow. You can choose which direction you want to assess the phase sensitivity to. So you add some inputs in those directions to the flow. We then track the evolution, or we then track the oscillation of the system till it reaches some limit cycle steady state. And then we compute this phase sensitivity function. Now the phase sensitivity function is nothing but, the phase advance or the phase delay that is caused by this impulse response trajectory compared with the baseline. So this, you have to trust me on this, but this model works really, really well for periodic flows, right? So just by having this information of the phase sensitivity function for these different forcing functions and then multiplying them with, any force of the system, you can immediately see the effect of forcing on particular phases of the system and how it affects the phase dynamics of the oscillation of periodic flows. All right. Now, I have one more intrusive technique to discuss in this reduced order modeling lecture. But before that, a quick recap on POD again. But what I want to draw your attention here is the fact that conjugate POD modes can serve as what is known as modal oscillators, right? So these modal oscillators are, systems that evolve at a particular frequency. And you can see that A1 and A2 evolves in a periodic manner with a particular frequency. And similarly, A3 and A4 and A5 and A6 and so on and so forth. So we can leverage this concept of these, when we do the POD decomposition, we are getting, these conjugate mode pair representation to build a network oscillator model. So First, what we can do is we can represent an oscillator with a complex number z, but of course this complex number z evolves in time, and what this is, so for mode 1 and 2, you would have z1 is equal to a1 plus j, which is your complex number, a2, right? And in polar coordinates, it gives us the amplitude and phase of this oscillator system. And you can have multiple different oscillators depending on how many POD modes you use for your analysis. Now, once we define these oscillators, we can track the impulse perturbations that are introduced to these oscillators. So what we do is we track what is known as the normalized modal fluctuations that are induced because of the introduced impulse perturbations to these oscillators. So the reason we can track these modal fluctuations exactly is again because of the fact of POD modes are orthogonal, so you can just take an inner product of your realization of the flow with the POD modes, and you can exactly track the changes that are happening in these temporal coefficients. Once we have the time history of the evolution of the temporal coefficients or these modal perturbations, we can regress the dynamics to get a complex network dynamical system. Now, the network A, essentially what it does, it's a complex network. It encodes the energy transfer characteristic between the modal oscillators. So that's what it's doing. So let's see an example for cylinder flow. This model works really well compared to the Galerkin projection model for capturing, again, off-limit cycle transients. So if you see a certain theme here, you can see, there is a lot of scope in input-output modeling, and you can see that there is a lot of scope in building reduced order models or tracking these transients, off-limit cycle transients. The limit cycle is well explained by the Galerkin projection model. But if you can explain the transients of the limit cycle or evolution from unstable equilibria, now that's a powerful reduced order model. So in this model, we can capture these off-limit cycle transients. Now, when you see the network structure, you can also see some amplitude and phase relationships between the modes. In particular, we see that the oscillator 1 contributes a lot to the dynamics. And this makes sense because oscillator 1 is the most energetic oscillator. And you can see that the higher order oscillators actually receive a lot of information from these, most energetic oscillators. Again, kind of an intuitive explanation that energy actually flows from these, energetic modes on to the lower energetic modes, essentially. All right, so a quick recap on what we covered in this lecture. We started with discussing one of the standard reduced order models in Galerkin projection. Then we discussed some themes about the sparse, performing sparse regression or the sparse identification of nonlinear dynamics. Then we discussed some intrusive models in eigensystem realization, phase-based model, and network models for describing the flow evolution in a data-driven manner. So all of these are data-driven reduced order models. Now, one key concept that is missing in most of these models is what about turbulence? So that's what we're going to talk next. Next up, we're going to talk about turbulence modeling. See you there.